Okay, this is the old one from last year when so I've included it because we're looking at mass spec now too. So the spectra of a compound whose empirical formula is C2H4O. So if we look at the size of that, when we put 2 carbons, 4 hydrogens and an oxygen together, that would have the molecule would be a size of 44 relative molecular mass. And when we look at the mass spec, we see that there's a parent peak for the whole molecule at what would be double that, 88. So the actual real molecule is twice the size. So that's the main thing that we use mass spec for, to find out the size of the actual molecule. If you ever had to quote this, you would have to quote that it was caused by this ion. So we know we're playing around with 4 carbons, 8 hydrogens and 2 oxygens, and there's lots and lots of different molecules that can fulfill that. So if we drew a few, 4 carbons, it's got the 4 and 8 means that there's a double bond somewhere. So we could just have a double bond like this, and we've got 2 oxygens, so you'd have to put the 2 oxygens somewhere. So, I mean, you could do things potentially like that. Have two hydroxyl groups. But anytime that you see 2 oxygens, you're kind of thinking that it could be an ester, or it could be a carboxylic acid. So this one's got 4 hydrogens, so we would have to put, if it was an ester, we could have our Q just it being from a methanoic acid originally, and then the other carbons could be a propanol, like that. And then you could do this systematically, where you took one of those carbons off and put it on here to make it ethyl ethanoate as opposed to propyl methanoate. And then you could take another one off and put it on here, so you could have methyl propanoate. You could also take this off here and put it on there and make a branched ester, which we don't name. Or you've got your 4 carbons in a line making butanoic acid. Or if we took one off here, we could put it on there and make what our molecule actually is. So you need to be able to kind of put different combinations together to work out what the problem, to work out the problem. They have done this molecule in the past. I can't remember if it was this one or if it had more carbons, but they have done an alcohol and a ketone together. Alright, so how do we know it's this molecule? What's the evidence? So the first bit of evidence, the mass spec, we could break the mass spec up and look at the fragments, but really the main reason that you look at that is to see how big the molecule is. So the IR is the next one that you would look at, and that will tell you some of the functional groups. So around 3000 here, this peak here, is the carbon-hydrogen bond, and then the peak to the side is the OH, and the OH has moved down further this way because it's an OH for an acid. And we've also got the sharp peak here at 1700 for our carbonyl, so those two things together would imply that it's a carboxylic acid. If this was further up and separate, so further up, and then you had the CH separate, oops, like this, then it could be an alcohol. And if you have a really, really short kind of skinny peak here, then that could be the alkene as well. Alright, so we can tell from this that it's a carboxylic acid. And if we look here, we've got hydrogen NMR because the numbers are smaller, and it's their chemical shift, ppm. And here you can tell that it's IR because we've got it's light, infrared spectroscopy. So infrared light, so wave length being turned into wave number. So this is spectroscopy and these are NMR. This one's hydrogen because the numbers are smaller, and this one's carbon because the numbers are quite big. Carbon is not split, so we've got 4 hydrogens that we're carbons that we're playing around with, and yet we've got only 3 peaks, which means that 2 of the carbons have to be in the same environment, because we've got less peaks than we have carbons. And one of the carbons doesn't even have hydrogens on it, so it's our carbonyl, which means our 3 carbons are only in 2 environments. So if you've only got 2 environments, it implies symmetry or branching. Okay, so if it's branched, then these 2 on the 1 carbon are in the same environment. So the carbon NMR helps us work out the branching. And if we look at the peak splitting here, oh, I've drawn it there actually, then these are due to the CH3s. So there's 6 hydrogens in the same environment. So this whole peak, the area is due to 6 hydrogens, which is like 2 CH3s. So the 2 CH3s are in the same environment, 6 hydrogens. And the reason that it's got a doublet is because n plus 1, the number of carbons, sorry, the number of hydrogens on the adjacent carbon, if we had 1 hydrogen on the adjacent carbon, then 1 plus 1, we have 2 peaks. So this equals the number of peaks. So if we have 2 peaks, 2 minus 1 will tell you how many hydrogens are on the adjacent carbon. So we've got 1. So 2 minus 1, got 1. This one's a septet, so there's 7 of them here. If we look here, septet, there's 7 little peaks. 7 minus 1, we've got 6 hydrogens on the neighbouring carbons. So this 1 hydrogen has got 6 neighbours. And the singlet here, this is got no hydrogen neighbours, so it's not split, so it's a singlet. So when you're writing it, you need to refer to how you worked it out. So the molecular formula is that, because the parent peak at, and quote the where you find the peak, so the mass spec, we found it at MZ88, and it's twice the size of the empirical formula, so that our empirical formula C2H4O1 must actually be C4H8O2, so the real formula. And then the IR told us that we had a broad, strong peak, so use the language, a broad, strong peak. And then because you know it's a carboxylic, quote the range, and it's lower than an alcohol hydroxyl group. If you look up the data booklet, it's between 2,500 and 3,500 for hydroxyl groups for carboxylic acids. Yep. And there's also a sharp peak at 1,700. Sharp peak at 1,700 for the carbonyl. So you could look up that and quote it exactly. it's hard to read the graph to say it's exact, but you could quote it exactly. So we were looking at the acid here, the carbonyl around 1700, so it's 1680 to 1740. And use your units when you're quoting it, so it's centimeters to the -1. So always use your units. Okay, sorry. So the molecules of carboxylic acid. There are only 3 peaks on the carbon NMR, so the 4 carbons are in 3 chemical environments. One is this, so the other 3 are in 2 environments, which implies branching. So 2 of them have to be in the same environment. The peaks at 1.15 have 6 hydrogens. So how many hydrogens are in that environment? There's 6. That's the whole area. And it's on here too, it helps you. Relative peak area, 6. Due to 6 hydrogens, 2 lots of CH3s. And it's adjacent to a carbon with 1 hydrogen because it's split into a doublet. So the number of peaks, 2 minus 1 equals the number of neighbours. So the number of neighbours plus 1 equals the number of peaks. The number of peaks minus 1 equals the number of neighbours. So the molecule has a CH3 to CH, which also fits, so that 6 hydrogens next to 1 neighbour. And this also fits the peak at 2.6, which has 1 hydrogen, which is split into a septet. 1 hydrogen split into a septet by its 6 hydrogen neighbours. And then I've run out of room, but the last thing that you could say is that you've got a singlet way up here, and the only thing that you would get a peak for right up there is a carboxylic acid one. Where did I put the... Yep, carboxylic acid is the only one that has a peak right up there. Okay.